Okay, hello everyone, and welcome to Lecture 6 of Computer Architecture. Today we're going to talk about combination logic blocks. Specifically, we're going to look at common combination logic blocks that we use when we build circuits, and these are blocks that we will also use later on in the course when we start building a processor. So let's get started. Before I start, a quick review of what we did last time. Last time we continued our discussion of the fundamentals of logic design, which was still part 1 of the course. And we looked at 4 variable Carnot maps, which was a continuation of the 2 and 3 variable Carnot maps that we saw in the previous lecture. And we saw an example of how to use a 4 variable Carnot map in order for us to simplify a 4 input logic equation. And we also looked at don't cares, which were cases where we didn't care what the output was because maybe the input combination is something that was not likely to occur, or that would never occur. And we saw how we dealt with don't cares inside of a Carnot map, and we saw how we can use our don't cares as 1, or we can use them as zeros, depending on whichever is convenient and whichever gives us a more efficient equation. We finally looked at canonical forms, and we saw that so far we were expressing the equations in terms of sum of products, but another canonical form is product of sums. And we saw how every row in the truth table has a corresponding minterm whose value is 1 for this row but 0 for all the other rows, and it has a corresponding max term whose value is 0 for this row and 1 for all the other rows. And we saw how a sum of products for a certain output can be expressed as the sum of minterms for which that output is 1, or it can be expressed as a product of the max terms for which that row is 0, or the output is 0. And then we looked at how we can use a Carnot map, just like we use the Carnot map to generate a sum of products. We looked at how we can also use a Carnot map to generate a product of sums, a simplification of a certain logic equation. And then finally, we looked at universal gates, and we saw how we said before that and, or not together can be used to represent any logic equation. However, and alone or alone or not alone are not sufficient. On the other hand, a universal gate is a gate where this type of gate alone is sufficient to build any circuit. And we looked at NAND and NOR gates as examples of gates that can be used to express any circuit. And we saw how we can map any kind of gate to a NAND gate. So a NOT gate can be represented as an AND gate, an AND gate can be represented as a NAND gate, and an OR gate can be represented with NAND gates. And most interestingly, we saw how we can take a product of sums where we have AND gates feeding an OR gate and convert that to NAND gates feeding an AND gate. And similarly, we also did the same thing for NOR gates. We saw how a NOR gate is a universal gate and can be used to express NOT gates, OR gates, and AND gates. And most interestingly, a product of sums where you have OR gates feeding an AND gate can be also expressed as NOR gates feeding a NOR gate. And that was a quick review of what we covered last time. Does anybody have any questions about last time's material before we move on to today's material? Okay, so someone was asking, how can we represent a function similar to the one in the assignment using just NAND gates? Well, you should already know how to express it using a sum of products. So if we go back here, you should already know how to express an equation or draw a circuit using AND gates and an OR gate, right? You know how to get a sum of products simplification of an equation and then draw the corresponding circuit for that equation. And using NAND gates is kind of very straightforward extension of this. So rather than having AND gates feeding an OR gate, you just have NAND gates feeding a NAND gate, and everything else is the same. And if you have inverters at the inputs of these AND gates, then you can use an AND gate with a single input to represent an inverter. Okay. Any other questions? If there are no other questions, then let's get started with today's material. So like I said, today we're going to look at common combination logic blocks that are used in circuits frequently. So the first block we're going to look at is a decoder. So what is a decoder? A decoder is a logic block that has n input signals and 2 to the power n output signals, where only one of the output signals is 1 for each input combination. So for example, we have a 3 to 8 decoder, so 8 is 2 to the power 3. So a 3 to 8 decoder has 3 inputs, and it has 8 outputs. And for every input combination, we're going to have one of these output values be 1, and the rest are going to be 0. So for example, if I pass 0, 0, 0 as an input, then I'm going to have out 0 be 1, and all the others are going to be 0. If I pass 0, 0, 1 as the input, then we're going to have out 1 be 1, and all the others be 0. And if we have 0, 1, 0, so this is the binary value for 2, if you guys remember binary to decimal conversion. So if I have 0, 1, 0 as my input, then out 2 is going to be 1, and all the others are going to be 0. And this goes on to all the combinations. So when I get to 1, 1, 1, this is going to correspond. So 1, 1, 1, 1, 1, 1 in binary is equal to 7 in decimal. So here when we have 1, 1, 1, then out 7 is going to be 1, and all the others are going to be 0. By the way, this representation here on the right, where one bit is 1 and all the others are 0, this representation of numbers is called one-hot encoding, and we'll talk later about where decoders are used for. But this is what a decoder is. Okay, so let's look at an example of a decoder. Example decoders. So a 1 to 2 decoder, a decoder with 1 input and 2 outputs. So for this decoder, if my input was 0, then out 0 is going to be 1, and out 1 is going to be 0. And so out 0 is going to be 1, and out 1 is going to be 0. And if my input was 1, then out 0 is going to be 0, and out 1 is going to be 1. So here, if the input was 1, out 0 is going to be 0, and out 1 is going to be 1. So here you can easily see that if I wanted to represent out 0 in terms of n0, then out 0 is just the inverse of n0, right? Because when n is 0 is 0, out 0 is 1. When n0 is 1, out 0 is 0. So out 0 is just the inverse of n0. So this inverter gives us out 0. And then out 1 is actually equal to n0. So because when n0 is 0, out 1 is 0. When n0 is 1, out 1 is 1. So out 1 can just be a wire from n0. Okay, so this here is on the right is how we can implement a 1 to 2 decoder. Okay, let's look at a bigger example. So a 2 to 4 decoder looks like this. We have 2 inputs and 4 outputs, because 2 to the power 2 is 4. And here our truth table is going to look like this. We can have different combinations: 0, 0, 0, 1, 1, 0, and 1, 1. In 0, 0, out 0 is going to be 1, everything else is going to be 0. For 0, 1, out 1 is going to be 1, everything else is going to be 0, etc. So here in 1, 1, out 3 is going to be 1, and everything else is going to be 0. Okay. So again, let's see how we can implement a 2 to 4 decoder. Well, if we look at out 0 is 1 when n0 and n1 are both 0, 0, and it's 0 otherwise. So we can implement this using so out 0 is 1 when we have not n0 and not n1. So this is how this AND gate over here with 2 inverted inputs is going to give us out 0. Okay, and similarly, out 1 is since out 1 is 1 in this case and 0 in all the other cases, then it's going to be not in 1 and not in 0 and in 1. Out 2 is going to be in 0 and not in 1, and out 3 is going to be in 0 and in 1. So we're going to get something like this, where we have an AND gate for each of the outputs, and this AND gate takes a combination of the input and inverts them based on kind of which row it corresponds to. Okay, we can even look at a bigger example. I'll do this one quickly. So we have 3 inputs, 2 to the power 3 is 8, so we're going to have 8 outputs. The truth table looks like this. We have 8 combinations of inputs, and for each of these combinations, we're going to have one of the outputs be 1 and all the others be 0. And similarly here, out 0 is going to be 1 when all three of these are 0 and it's going to be 0 otherwise. So at 0 is going to be not in 0 and not in 1 and not in 2. So it's going to look like this. We're going to have an AND gate where we have not in 0, not in 1, not in 2, and that gives us out 0. And just like before, each of these outputs corresponds to one of the combinations in the input. So each of them is going to have its own AND gate with a different combination of inversions. So it's going to look like this. We have an AND gate for each of these outputs, and where we put the inverters depends on what input it corresponds to. Now, one thing that you probably noticed about this is that each one of these outputs corresponds to a minterm, right? So remember how we said that each one of these input rows has a corresponding minterm that is 1 for that row and 0 for all the other rows. Well, here you can think of a decoder as each output of the decoder be corresponding to one of the minterms in the truth table. Okay, so a decoder essentially, if we take a decoder gives us all the minterms for an input combination. Okay, and because each of these outputs corresponds to a minterm, we can actually use a decoder. That's not the only use of a decoder, but we could use a decoder to implement any circuit if we combine it with an OR gate. So let's look at an example of this. Again, this is not the only use of decoders. We'll look later about where we use decoders inside of circuits. But it's just interesting to observe and a demonstration of how decoders work to see that, since every output of a decoder is a minterm, we can cascade a decoder with an OR gate to implement any logic block. So if we go back to this truth table over here for our car warning system, we saw that we have all these combinations, these 8 combinations, and for each of these combinations, the output's either 0 or 1. So what we can do to implement this, if we had a decoder, if you went to the lab and it turns out all you have is a decoder and OR gate, what you could do is you could pass the inputs to a decoder, D, K, and L. You can pass the inputs to a decoder. And then for B, you would have an OR gate that gives you B. And you would pass to this OR gate all the lines where the output is 1. Okay. So here, what we would do is for this row over here, the second row, we would pass the line from the second output of the decoder. For the for the last 3 rows, we would pass lines from the last 3 outputs of the decoder. And by doing this, what we've done is we've essentially implemented this circuit over here using a decoder and an OR gate. Okay? And the reason this works is because each of these lines of the decoder corresponds to a minterm. So if we take the line corresponding to each of these rows, we get all the minterms inside of the OR gate. And remember that the equation for B can be expressed as the sum of all the minterms. Okay. Any questions about how we use the decoder to implement this circuit? Of course, this is not necessarily the most efficient way to implement the circuit because over here we have many outputs of the decoder that are not used. Which means that we have a lot of AND gates inside of the decoder that are not used. But if it happened to be the case that in the lab all you had was a decoder, or you were already decoding D, K, and L for some other reason, so you already had the decoder, then this is where it would be a good way to implement the circuit using the decoder. Okay, so if there are no questions on decoders, let's move on to the next circuit of interest, which is multiplexers. So a multiplexer is a logic block that selects one of multiple input signals based on a selector signal. So this is a common operation that we do all the time. We have some input signal, some condition, or some value, and based on that value, we would like to select one of multiple inputs. The circuit to do this is called a multiplexer. So a multiplexer looks like this. we have multiple selector signals and we have multiple inputs. Here we have 3 selector signals. So with 3 selector signals, we can have 2 to the power 3, which is 8 combinations. So we're going to have 8 inputs to the multiplexer, 1 for each possible combination of the selectors. And ultimately, we're going to have 1 output because we're only going to use the selector signal to select one of the inputs to be the output. Okay? And let's look at an example of how this works. If I set my selector signal to 0, 0, 0, then the output is going to be equal to N0. If I set my selector signal to 1, 0, 1, for example, so 1, 0, 1 is in decimal is 5, so my output here is going to be my 5th input, which is N5. Okay, so this is an example of how multiplexer works. Let's look at how we can implement multiplexers. So here, a 2-input multiplexer is going to have 2 inputs, and it's going to have 1 selector signal because 2 to the power 1 is 2. Of course, all multiplexers are going to have 1 output. Okay, and let's see how we can implement this. So the way we can implement a multiplexer is we can have an AND gate for each input. Okay, and we OR these AND gates into an OR gate that is 1 output. And essentially what we would like to do is when the select signal is 0, we would like to set this and the other input for this AND gate to 1 so that we let N0 pass because N0 and 1 is going to be N0. And we would like to select the input to this other AND gate to 0 because we would like to pass N0, we don't want to pass N1. Okay, so this is how we do that. When we do this, we put an inverter here and we just pass a line over here. So here, when select is 0, this signal is going to be 1, so N0 is going to pass. And when select is 0, this is going to be 0, so N0, the output here is going to be 0, so N0 is what's going to pass. And when select is 1, the output here is going to be 0, so the output here will be 0, so nothing comes from here. But when select is 1, the output here is 1, so the N1 and 1 is going to be N1, so here the output is going to be N1 or 0, which is N1. Okay, did someone have a question? Hello, did someone have a question? So someone's asking if we can use a decoder followed by ANDs for the signals to build a multiplexer. Absolutely, you can do that, and I will actually talk about that soon. So let's look at another example. At 4-input multiplexer, so this is going to have two selector signals, and 2 selector signals gives us 2 to the power 2, which is 4 combinations. So we're going to have 4 different inputs to select from, and the result is going to go to the output. And we're going to use the same strategy. We're going to have an AND gate for each one of the inputs, and we're going to have pass these AND gates all to 1 OR gate, which is going to be the output. And then what we're going to do is we're going to pass the selector signals to different AND gates, which will control which AND gate gets the output. So for example, if my select signal is 0, 0, then here not 0 and not 0 means 1 and 1. So the output here will be 1. So N0 will pass from here. But if you look at all the other gates, here we're going to have 0 at this input of the AND gate. So the output will be 0. So the output of this AND gate here will be 0. Same thing here, we're going to have a 0 over here. So the output of this AND gate will be 0. And what that means is that the output of this AND gate will be 0. And then finally here, both of these will be 0. So the output of this AND gate will be 0. So the output here will be 0. So we're going to get N0 or 0 or 0 or 0, which means that the output is going to be equivalent to N0. Okay? And you can kind of do the same exercise for the other inputs. If my selector signals were 0, 1, then this AND gate will have a 1 on the output. All the other AND gates will be 0, which means this AND gate over here will have N1 on the output, and all the other AND gates will give 0. And I'll have N1 or a bunch of zeros, which will give me N1 at the output. So as someone correctly observed, this part of the circuit on the left is actually a decoder, right? So if you remember, here we have a decoder, because what we're trying to do is we're trying to take the select signal and convert it to where we have a 1 for the input that we want and a 0 for all the other inputs. And that's exactly what a decoder does. So this here is the decoder. This over here is a 2 to 4 decoder, right? It takes two signals, gives us one for one of the outputs and one of the AND gates, and 0 for all the others, so that we end up selecting one input. So the way that we can implement a multiplexer is by having a decoder and then followed by these AND gates and the OR gate. Okay. So if we want to implement a 8-input decoder, we're going to have 3 selector signals. 2 to the power 3 is 8, so we have 8 combinations corresponding to 8 different inputs that we want to select from. And the way we're going to do it is we're going to have an AND gate for each one of the inputs that all feed into an OR gate, and then we're going to have a decoder that takes the selector signal, decodes it to where we have 1 for one of these inputs and 0 for the others, and that input is the one that's going to pass into the OR gate. Okay? Any questions about how we implement multiplexers and what they do? All right, if there are no questions, so we can, just like we can build any logic block from a decoder and OR gate, we can actually also build any logic block using multiplexers and just some inverters if we need to. So for example, the way to do this is if we have 3 inputs, D, K, and L, what we can do is we can take, if we have n inputs, we take n minus 1 as the selector signal. So if we have 3 inputs, we're going to take the first 2 inputs as the selector signal, and we're going to pass the third input as the input to the multiplexer, depending on the values in the truth table. So what we're going to do here is we're going to consider D and K as our input signal. So here we're going to notice that when D and K are 0, 0, B is the same as L, right? So here when L is 0, B is 0. When L is 1, B is 1. So when D and K are 0, 0, then B is equal to L. When D and K are 0, 1, then here we notice that in both cases, regardless what L is, B is 0. So here B is equal to 0. When D and K are 1, 0, then in this case, again, we have 0 for L is 0, 1. We have B is 0, 1. So here B is equal to L. And when D and K are 1, 1, we'll notice that B is 1 regardless of what the values of L is. So here B is equal to 1. So the way that we can use a multiplexer to implement this circuit specified by this truth table on the left. By the way, if you guys remember, this is our car warning system example. What we can do is we can simply have a multiplexer where our input signals are D and K. And for the input that corresponds to dk being 0, 0, we're going to have L. So because we know that when D and K are 0, 0, B is equal to L. For the input that corresponds to 0, 1, we're going to have we're going to have 0, so that B will be 0 in this case. For the one where dk are 1, 0, we're going to have L corresponding to B equals L over here. And then finally, for the last one where dk are 1, 1, we're going to have B equals 1. Okay, so we're going to put a 1 over here. So this is how we can use a multiplexer to implement the circuit specified by this truth table on the left. Now again, this is not necessarily the most efficient way to implement this circuit. Okay, it's not necessarily the most efficient way to implement this circuit. However, if it happens to be the case that you go to the lab and all you have in the lab is a multiplexer and maybe some inverters, because it could be the case that one of these is not L, right? So if all you have in the lab is multiplexers and inverters, then what you can do is you can use these to implement the circuit that you want, rather than having to go and get something else. Okay, any questions about how I use the multiplexer to implement the circuit? Okay, so if there are no questions, let's move on to the next, or before that, let me talk about multi-bit multiplexers. So in many cases, when we want to select something, a lot of times operations are performed on multi-bit signals, not just one signal, and we want to select multi-bit inputs. So for example, we might have a case where we have, an 8-bit number or a 32-bit number, and I might want to be able to select between two different 32-bit numbers. So in this case, to select between two different 32-bit numbers, what I will need is I will need a multiplexer for each one of these bits. But those multiplexers are all going to have the same selector signal, but they're just going to have different input signals. And rather than drawing in my circuit 32 different multiplexers, we have a shorthand way of drawing this. We have a bus. A bus in a circuit diagram is essentially a collection of wires that are treated as one signal. So here, if you see something like this in a circuit diagram where I have a line and then I have this dash on it with n, this refers to an n-bit bus. So what we mean by this line is that this is n different lines that are all treated as the same signal. And a lot of times we use multiplexers to select between multi-bit signals. So rather than drawing n different multiplexers, we will draw one multiplexer and we will make the input to this multiplexer a bus of n signals, and then we have a selector signal that selects which one of these buses we want to take our input and give out as the output. So in practice, this will be n different multiplexers, each selecting one input signal. But for short and for concise representation, we just represent it as one multiplexer with a bus as input and a bus as output. Okay. So it's good to be aware that when you see this kind of representation in a circuit diagram, this means a bus or an n-bit a wire or n different wires treated as one signal. Okay, next let's look at another kind of commonly used circuit that can be used to implement different logic blocks, and that's a programmable logic array. So if you recall, any logic function can be expressed as a sum of products. Any logic function can be expressed as a sum of products. So what a programmable logic array is that it's essentially a device consisting of, we have a set of inputs and all their complements. So we have n inverters. We have a stage with up to 2 to the power n AND gates. And then we have a stage with m OR gates that produce m outputs. So these 2 to the power n AND gates feed into these m OR gates to produce m different outputs. And the connections between the AND gates and the OR gates are programmable, so that different people can come and program this programmable logic array in different ways to implement different kinds of circuits. Okay, and we can use a PLA to express any logic block that we want. Of course, assuming that we have enough AND gates inside of the PLA to represent our circuit. So let me show you an example to make this a little more clear. The layout of a PLA is going to look like this. So if I have a 2 input, 2 output PLA, what we're going to have is we're going to have 2 inputs, and each of these inputs are going to have inverters. So we have 2 inputs, and here over here we have 4 lines corresponding to the input, each input and its inverse. And here we have in1 and its inverse. And then we're going to have a certain number of AND gates, up to the power n AND gates. So here we're going to have 4 AND gates, okay? And these AND gates are going to be crossed with these inputs and their inverses. Now, there's not going to be a connection here by default, but a programmer can come and kind of burn a connection over here or program a connection over here if they would like this input to go into this AND gate. And then finally, these AND gates the outputs of these AND gates are going to be intersected with OR gates. So we're going to have these OR gates that correspond to the 2 outputs. So we'll have an OR gate for each output. And again, we have this intersection here between the outputs of the AND gates and the inputs to the OR gates. Okay. Now let's see. Now by default, these wires are kind of intersecting, but they're not connected. And what we can do is we can, depending on the logic equation that we want to implement, we can create connections wherever we want them to implement our circuit. So let's look at an example. Let's say I had this truth table over here. I had the 2 inputs and 2 outputs, and I would like to use a PLA to implement a logic block that has this specification over here. Well, the way I would do that is first I'm going to extract the equations for each of these outputs, so I can see that I have, each row. I'm going to kind of code each row with a color to make things a little more clear. So we can see that here C is equal to not A and not B, or A and B, right? So C is going to be 1 if we have not A and not B, or if we have A and B. And D is going to be equal to not A and B, or A and not B. So here D is not A and B, or A and not B. Okay, so given these equations that specify this logic block, let's see how we can use this PLA on the left to implement these equations. So first, I need the term not A and not B. So I'll use the first AND gate to provide not A and not B. And to do that, what I need to do is I need to burn connections at the inputs of these AND gates where we have not A and not B. So we have not A over here, intersects with this AND gate over here, and not B intersects with this AND gate over here. So what I'm going to do is I'm going to create connections here and over here in order for me to have 2 inputs to this AND gate, which are not A and not B. Of course, I could have done this. I could have drawn connected not A over here and not B over here. It would be the same. What I want to do is I want to pass the output of this AND gate to the OR gate. So I'm going to burn a connection over here as an input to this OR gate. Next, I want to be able to get A and B. So what I'm going to do is I'm going to use the next AND gate to represent A and B, and I'm going to burn connections at A and at B. So now the inputs to this AND gate are A and B. And then over here, I want the output of this AND gate to go to C. So I'm going to program a connection at this point over here so that the output of this AND gate goes to C. Okay. And I'm going to do the same thing here, not A and B. So I'm going to use this AND gate over here to get not A and B. And then I'm going to pass that as an input to D by programming a connection here. And then A and not B, I will program this AND gate to have A and not B. And then I program, I want to pass the output of the AND gate to the OR gate for D. So I'm going to program a connection over here. And by doing this, what we've done is we've used the PLA to implement the specification on the right. Okay, any questions? Okay, if there are no questions, I'll move on. So let's look at, there's a shorthand way of drawing PLA diagrams. So rather than kind of drawing all these connections, all these lines, and all these lines over here, and all these AND gates and all these OR gates, a shorthand way of representing a PLA diagram is like this. We have a signal and its inverse stays, but then we're just going to have one wire here, and we're going to put the connections on the same wire, and we're going to have one wire over here, and we're going to put the connections on the same wire. Now, this is just a shorthand way of drawing the diagram, but in reality, what's going on over here is we have 2 different wires here, one that's connected to not A, one that's connected to not B, and we have 2 different wires over here, one that's connected to this AND gate, and one that's connected to this AND gate. Okay, this up here is referred to as the AND plane because this is where the inputs to the AND gates intersect with these inputs over here, and this down here is referred to as the OR plane because this is where the input to the OR gates intersects with the outputs of the AND gates. Okay. So someone has a question. Can we use OR with 2 inputs instead of 4 or no? Yes, we can do that. So that's actually what we did in the previous diagram. So in the previous diagram over here, even though this OR gate has 4 inputs because kind of it's provisioned to be able to connect to any one of these AND gates. But in this case, we only need to connect it to 2 of the AND gates, and that's why we only use 2 of the inputs. Okay, let's do a bigger example. So let's say we had these equations over here, and we wanted to implement these using a PLA. So here we have 3 inputs, A, B, and C, and we have 3 outputs, D, E, and F. So we're going to use a 3 input, 3 output PLA, where our inputs we have A, B, and C, and our outputs are D, E, and F. And we're going to have, well, let's first program A and B. So we need A and B as one of the terms, and that's going to go to D. So here for the first line, we're going to make that A and B. So we're going to have A over here and B over here, and we want that result to go to D. So we're going to have program a connection here. Next, we want not A and not B. So we will use the second line for that. We have not A and not B. And then we want also that to also go to D, so we will program a connection over here. And then finally, we want C, so we're just going to have C as the only input to the AND gate. And in this case, we're also going to pass that as an input to the OR gate. Okay? And that's going to be the result for D. Next, we want E. So E also uses not A and not B. So since E uses not A and not B, I don't have to create another. I already have not A and not B. I don't need to create it again. So what I can do is I can also pass this not A and not B to the as an input to the OR gate for E. And this is an important aspect of PLAs, which is being able to reuse these AND gates. So sometimes it may be the case that the most efficient equation for each of these is not necessarily the best one to use. I might want to use different equations where we have more terms in common between D, E, and F. Okay, that might give us a better result. Okay, but that's a detail that you don't have to worry about in this course. So here we have not A and not B. We have not A and C. So we're going to use this fourth line to program not A and C, and we're going to pass that as an input to E. And then finally, we have A, B, and not C. So we're going to have this fifth line here to program A, B, and not C. And that's going to go as an input into the E OR gate for E. And then finally for F, F also uses A and B. So we already have A and B. We don't need to create it again. So we can burn an input, program an input over here, connection over there. We have not A and C. So we already have not A and C from before. So we can program a connection over here. And then finally, we need A and not C. We don't have that. So we're going to use this last line here to program A and not C and pass that as the last input to the OR gate for F. Okay? So this is how we use the PLA to implement this circuit, this specification over here. Any questions? All right, I'll do a final example, which was our running example, the car warning system. And if you remember, the equation for that was B is equal to D and K, or not K and L. So the way we would do that is we would have a line for D and K, and we would pass that to the OR gate for B. And then we have not K and L, so we would have over here not K and L, and we would program a connection over here to pass that to B. And by doing that, we can use a PLA to implement the circuit over here. So if you're in the lab, you have a PLA, you probably have some software that helps you program the PLA, and you want to implement a circuit like this, you can use a PLA to do that. Okay, so let's look at our fourth and last logic block that I want to talk about today, which is memory blocks. So a memory is a logic block that stores data. Okay, and the block for a memory looks like this. You have an address, which is going to be an n-bit value, and you have data at the output. So and you have data as input, and you also have this signal that specifies whether you want to read or write. So if you want to read, what you would do is you would provide an address, and you would set the signal to 0, so meaning you don't want to write, you want to read. And what happens is the value stored at this address in the memory block will be read as the output. And if you set this, if you want to write, what you would do is you provide an address and the value that you want to write over here, and you would set this to 1. And in this case, what would happen is the value that is passed here will be stored to the address that is passed over here. Okay, so let's look at some examples. Here, if I pass, if I have a a memory that has 2 address bits and 3 values. So if the memory has 2 address bits, it means it has 2 to the power 2 different address locations. And if it has 3-bit input, 3-bit output, what that means is that it stores 3 bits at each address location. Okay, so here if I pass in 0, 1 as my address location, and I pass in a 0 over here, which means I don't want to write, I want to read, what will happen is the memory will go to the location that corresponds to 0, 1, which is over here, and it'll look up the value stored at 0, 1, which happens to be 0, 1, 0, and it will give me this value as the output. And if I want to write, then if I pass, for example, the address 10 over here, and I pass a value that I want to write, and I pass a 1 over here, meaning I want to write, I don't want to read, then what will happen in this case is that I will take this value that I passed in 0, 1, 1 and store that at the address 10 here, 0, 1, 1. Okay, so I've updated the value that was stored inside of the memory. Okay. Now, there are different technologies for building memories, and these different technologies will be covered later. But today I want to look at a very specific type of memory. But before I look at that, does anybody have a question about memories in general? This idea of providing an address and providing some data and writing data at this address, or providing an address and reading the data at that address. Is that clear to everyone? Okay, so the memory block that I want to look at today is read-only memory. So a read-only memory is a type of memory where we can only read, we cannot write. So here we just have an address as the input, and it gives us data as the output. There's no write signal because we are never going to write, and there's no input data because we're never going to write. We only ever read from this memory. Okay, so the read-only memory is usually non-volatile, which means if you turn the power off, right, the contents of the memory will not disappear. Okay, if you turn the power off, the contents of the memory will not disappear. And obviously, it's from its name, it's read-only. So the contents can only be read. They cannot be modified after the memory is manufactured. Okay. So someone is asking, how is data initially written on the ROM? It depends on how the ROM is implemented. There are, in some ROMs, you might have kind of some technology that you can write once and then later on you cannot change it. In some ROMs, maybe the technology allows you to change it, but the circuit manufacturer doesn't let you change it. They don't provide you a way to change it. And in some cases, and I'll talk about later, we can actually use combinational logic to implement read-only memory. So rather than implementing it as a memory, we have the truth table that we want, and we implement it using AND gates and OR gates. Okay, that's a quick answer, but let's look at that in more detail. Okay, so we can actually use ROMs to implement logic blocks, right? So if I have So a ROM can be used to implement any logic block by simply storing the truth table of the logic block as the content of the memory. So for example, if I have a truth table like this, where my inputs are A, B, and C, and my outputs are D and E, right? What I can simply do is I can treat A, B, and C as the address bits of a ROM, and I can treat D and E as the output of a ROM. And in this case, what I can do is I can use a ROM to implement the logic block with this specification on the left. So rather than using AND gates and OR gates, I can just take this truth table over here, or the outputs of the truth table, and store them in a ROM, right? And here I would have an address for, since I have 3 different inputs, I have a 3-bit address, which gives me 2 to the power 3 different address locations. And in each location, I will store the value for the output. And this way, if I get a certain input, I will simply read the value at the output, and this will be my result. Okay, so I can actually use a ROM to implement a combinational, a combinational logic block. And the opposite is also true. If I wanted to implement a ROM, I might actually implement a ROM as a combinational logic circuit rather than using some memory technology. Okay, So I might take this, if I wanted to implement a ROM like this with these contents, I might think of this as kind of a truth table, then simplify the equation and implement it using AND gates and OR gates. So when is it, so PLAs versus ROMs, when is it better to use a PLA, when is it better to use a ROM to implement some circuit? So implementing logic blocks using ROMs requires you to store a value for every possible combination of inputs. On the other hand, with a PLA, you only need to have logic gates for the cases where you have true for the true terms. So this requires less logic. But the nice thing about ROM, so PLAs require less hardware than ROMs because ROM stores every possible output, whereas PLAs will only store the output when the case is 1, or if it's a PLA that does product of sums, it'll only store it. You only need to program the cases where the output is 0. On the other hand, the nice thing about ROMs is that you can implement any logic block where you have a matching number of input and output bits. But this is not necessarily possible with PLAs because PLAs don't only constrain you with a number of inputs and outputs, but they also constrain you with a number of AND gates that you have inside. So if you don't have 2 to the power n AND gates in a PLA, which you typically don't, then you may not, even if you have the right number of inputs and outputs to the PLA, you may not have the right number of AND gates that you need to implement your circuit. So this is where a ROM might be a better case, better way to implement a circuit than a PLA. Okay, and with that, that's the end of today's lecture. You can read more about the material we covered today in section B.3 in the textbook. Does anybody have any questions before we end? Okay, if there are no questions, then that is all for today, and I'll see you next time. Bye, everyone.